Bismillahirrahmanirrahim. Assalamu alaikum, dear students. We are now starting the lectures for week number 7 for wireless and mobile communications. This is our first lecture for this week. In our previous lectures, we have talked about path loss modeling and shadowing, and we discussed that the combined name of these two models is actually large scale modeling, and we had comprehensive discussion related to this large scale modeling, and we also discussed variety of different models. While discussing different model, I gave you an introduction that we can model model the wireless propagation through measurement campaigns. In fact, there has been variety of different models proposed in the literature which are based on different campaigns. Some of them they are very commonly used, and few of them they are very site specific, so they are useful for those specific type of environments. In today's lecture, we are going to talk about some of the measurement based models which are commonly used, and primarily the model that we are now starting for discussion is these are actually outdoor propagation model which were used to model the propagation environment in an outdoor cases. If you recall, in our initial discussion, we talked about the deployment of wireless communication systems, and you know that the initial development of wireless systems was primarily related to the providing coverage in outdoor environments. So this outdoor model that I am going to discuss in today's class is actually related to that type of environment, and which were based on the measurement campaigns by our research group led by Professor Okumura. First of all, before starting the discussion on Okumura model, let me quickly review what we have discussed so far related to the models. You know that the propagation the actual RF propagation in the urban environment, it depends on variety of different factors. Those factors are not only related to the wireless system but also the environment as well. For example, the frequency, if we change the frequency, the propagation losses gets changed. If we change the polarization, the propagation losses they get changed. The building geometry, the structure material, the orientation, height and density of buildings, all these stuff they affect the propagation in that urban environment, and eventually they result in different losses. So all these parameters they are related to the propagation modeling for an urban environment. In most cases, for deployment in our wireless systems, the base stations they are generally elevated. So we typically have base station height which is relatively large as compared to the street level or building levels in an environment, whereas the mobiles they are at almost they work at the human height, or you can take it as a street level for propagation modeling. So this is the common phenomena. This is the common architecture of the system, where you have relatively elevated base stations, but the mobiles they are generally handheld, and they are kind of at the lower level. For large scale path loss modeling, we know that our main objective is to find the path loss, or in other words, we are interested in calculating the received signal level, and we know that this received signal level is actually dependent on the propagation length. So we generally try to calculate this path loss in terms of the distance. As we know that the loss, it depends on the size and density of buildings. So generally we try to classify the buildings in different types of terrains that we will be discussing shortly, inshallah. So let us start the discussion on the Okumura model. This Okumura model is basically a measurement based model. Professor Okumura and his team, they planned a comprehensive measurement scheme in Tokyo in 1960, and they made a number of measurements at different antenna heights, different distances, and different types of environments. So and on the basis of those measurements they developed this model. The measurements that were carried out in this scheme was actually in this range, 200 megahertz to 1920 megahertz, although we can extrapolate up to 3 gigahertz, but this is the actual distance range which were used in that model. Oh, sorry, not distance range, frequency range. So this was the actual frequency range that was used in that model. So different measurements were used in this range, 200 megahertz to 1920 megahertz. The separation, transmitter and receiver separation, because it was an outdoor environment, so it was relatively large separation between transmitter and receiver. So measurements were taking in the range of 1 kilometer to 100 kilometers. So this model is typically applicable for this range. The basis station antenna heights were from 30 meter to 1000 meters. So different base station antenna heights were also used. The environment, as I discussed, because this the propagation is actually dependent on the urban environment, type of urban environment, how densely buildings are situated in certain environment. So in order to classify those urban environments, 3 classifications were used in this model. First one was open areas. Open area means where you had very lesser density of buildings, like for example in the farms or highways where you have seldom buildings. So this type of environment is actually an open area where the propagation is not significantly affected by the buildings. Suburban area are the areas where we have relatively higher density of building, like small towns where you have low density of building and low height of building. And third one is the urban area where you have relatively high and relatively longer building, and you have relatively higher density of building. Although this model, because it was based on the measurements done in 1960, is not truly represent modern cities, but still it is commonly used to have the comparison between different models. So it provides a good basis for the comparison. So as I said, there are 3 different types of building which were used in the classification of this model. First one is the open area model. This open area model represents a location where we have plenty of open space. There are no tall trees or buildings in the path, and typically we have a clear land up to 300 or 400 meters from the transmitter. So generally this type of environment was characterized by open area environment, or you can take an example of farmland as this environment. The suburban area model generally represent villages or highways where you have scattered trees and houses. There are and there may be some other obstacles in the propagation path, but those obstacles are not very congested, so density is relatively low. The third type of environment is urban area environment, where which generally represents built up cities, where you have large building and houses, generally with multi-storied building, or large villas which are very closely built, and we have thick and tall trees in the environment. So this type of environment is generally classified as an urban area environment. What Okumura model did, they chose urban area as a baseline model. So basically the formulas were developed for this urban area environment, and they applied some correction factors in order to convert the other classification. So if you are working in a suburban environment, what you have to do, you have to calculate the loss using urban area environment, and then you have to apply the correction factor to make the adjustment for suburban environment. So this is an overview related to this Okumura model. So what Okumura did, Okumura developed a set of curves which were giving a median attenuation related to the free space. So it's in formula, it's written as AMU. So how much attenuation is there in addition to the free space attenuation? Okumura developed some curve and formula in order to calculate that, and for that AMU calculation, they set the base station a height of 200 meters. So basically the formula was related to the base station antenna height of 200 meters and mobile antenna height of 3 meters. So if you have different height of base station antenna or different height of mobile antenna, so you may be required to make some corrections in the model that we are going to discuss in shortly. So these curves were developed on the basis of excessive measurements using those vertical omnidirectional antenna. So they used omnidirectional antenna both at the base station and the mobile station, and generally the transmissions were made in the frequency range from 100 megahertz to 1920 megahertz, but typically the formula that we use is from 200 megahertz to 1920 megahertz for a distance range of up to 100 kilometers. So in order to determine the path loss model using the Okumura model, the first thing is to calculate the free space path loss between the transmitter and receiver. Then we have to calculate this median attenuation, AMU, which is also function of frequency and distance. It depends on the frequency and distance, and in order to calculate this AMU, we generally refer to some curves which I am going to show in a while, inshallah. And then depending on the type of terrain and depending on the type of antennas, we need to apply some correction factors as well in order to calculate overall models. So this is the overall procedure. So first thing is the free space path loss model that we have already discussed previously in detail. So I understand that you can easily calculate the path loss occurring from the free space model. The second thing that we need to use is this median attenuation. As I said, Okumura has developed a formula and curve for this median attenuation. So this is the overall formula for the median path loss using the Okumura's model. So L50 is actually referring to the median or 50th percentile value of the propagation loss. So this is actually the median value of the propagation loss that is calculated from the Okumura model. The first part is this LF. You can see that this LF is same as the free space propagation loss, as I discussed briefly. So this LF is based on the free space propagation, which can be calculated using the free space propagation model. This AMU is that median attenuation relative to free space, which we will calculate using the curves developed by the Okumura, I will show in a while, inshallah. Second, because for model, the reference point was used at for base station, the reference antenna height was 200 meter, and for the mobile antennas, the reference antenna height for 3 meter. But practically the antenna heights can be different from the reference antenna heights. So if there is a difference in the reference antenna heights, that is base station height is different than 200 meter, or mobile antenna height is different than 300 meters, in that case some correction need to be made in this loss. So these two terms, they are related to the correction factor or gain factor occurring from the base station antenna height and received antenna height. So GHTE is actually the base station antenna height gain factor, and GHRE is the mobile antenna height gain factor. So these two are dependent on the height of the antennas, base station and the mobile. G area is the gain because of the type of environment that you are using, because the reference was the urban environment. If you are using some other type of environment, in that case some correction factor or this gain factor need to be applied in this model. So this comes from that correction. So this is these are the terms that need to be calculated in order to calculate the Okumura model. There is one thing you need to notice, that this antenna height factor, this GHTE and GHRE, they are actually based on the heights of received antenna and the transmit antenna, and they are not dependent on the antenna pattern. So these are not the typical antenna gains that we discussed previously. These are actually referring to the correction factors which are coming from the height of the antennas, not from the radiation pattern of the antennas. Okay. So these are the correction factors related to antenna, both transmit antenna and receiver antenna. The first expression is related to the transmit antenna. So if we have transmit antenna GHTE, so we use this correction factor here, whereas we have this transmit antenna or base station antenna whose height is more than 30 meters up to 1000 meters. So this expression is valid for this range. So if your base station antenna height is different than 200, so you would get some value for this, which need to be applied to this expression in order to get the total loss. You can see that if I substitute HTE to be equal to 200, so this 200 would be equal to 1, this 200 upon 200 would be 1, and log of 1 is equal to 0. In that case there is no correction factor needed. This term goes to 0 when you have base station antenna height of 200, which is evident from this assumption that we have based our model on the reference point of 200 meters. So this is a correction factor which is related to the base station antenna. Similarly, these are the correction factors which are related to the mobile antennas, and you can see that there are two different expressions depending on the height of antenna. If antenna height is smaller than 3 meter, in that case we have to use this expression. If height of antenna, the mobile antenna, is greater than 3 meters, in that case we have to use this expression. So these two expressions they depend on the height of receive antenna. So if receive antenna height differs from the 3 meter height, you can calculate the correction factor using this formula. Again, you can see that if I substitute HRE to be equal to 3, which is the reference value, so this term goes to 0. Okay, so this was the discussion related to these gain factors. Now let us move on to the other terms. which is this median attenuation factor, which is function of frequency and distance both. You can see here this AMU, this is actually dependent on frequency and distance. What Okumura did, they made a graph or multiple curves for different frequencies and different distances, and on the basis of those curves you can calculate this median attenuation. You can see that this horizontal axis here, this one is representing frequency. This is frequency in megahertz, starting from 100 megahertz up to although the model is up to 1920, but as I said, it can be extrapolated up to 300 megahertz. So this frequency is going up to 300 megahertz. This axis, this intermediate part, this is actually representing distances. You can see the distances from here as well. These are representing the distances from 1 kilometer up to 1000 kilometers. So these are distances from 1 kilometer to 100 kilometers, all in kilometers. These distances are in kilometers, and you have different curves here in order to see the median attenuation. You have to look at this axis here. This axis is actually representing the median attenuation. So say for example, if I want to find what is the median attenuation at 200 megahertz. So for 200 megahertz we have this value, you can draw a line here. Let's say if I want to find the median attenuation at, say for example, 10 kilometers, so you can take the line here. So this curve here is actually representing the 10 kilometer. So the point where it intersects, you can check the value for the median attenuation on this axis. So this axis gives you the median attenuation. So you can see that our this point would be representing the median attenuation relative to 200 megahertz and 10 kilometer distance, and this is roughly around maybe 26 decibels. So in this way, these curves can be used to calculate the median attenuation whenever you know the frequency in megahertz and distance in kilometers. Okay, this is the correction factor curves for the area factor. The last term in the formula here, you can see, you can refer back to this formula here. The last term G area is represented by these curves here. Actually, as I said, for urban environment we do not need any correction because of the curves that I showed previously. This one, they are based on the propagation in urban area. So this curve is actually related to urban environment. So whenever we have urban environment, we do not need any correction. But whenever we have some different environment, in that case we need to apply some correction. So the correction is dependent on so we have three different curves: suburban area, quasi-open area, or open area. Quasi-open area is somewhat in between suburban and an open area, where you may have a low density of trees or buildings. And in similar way to the previous curve, you can calculate the correction factor by identifying the appropriate frequency. For example, if I intend to find the correction factor for suburban area at 200 megahertz, so I can draw a line here, and you can see that the correction factor would be around 6 decibels. You can read it from this vertical axis. So in this way, this curve can be used to represent the correction that is required when you are working in any other environment for other than the urban area. So summarizing important points related to the Okumura model, this Okumura model is basically is primarily based on the measured data. So there is no analytical explanation or mathematical calculation behind that. there were measurements taken in an actual environment, and the model was developed by fitting those measurements to these analytical the curves that I showed previously. For some cases we can extrapolate the curves, but generally this model is valid for the specific ranges that I showed previously, but sometimes we can extrapolate if the change is kind of smooth. So this model is actually very simple to use and best in terms of accuracy, that it gives a good estimate of the path loss in different types of environments. This model is very practical because it is of simplicity, and it has become standard for system planning in Japan. Basically, it was it was developed in Japan as well, and it was used in Japan for system planning and path loss calculation. So this model, although there are certain advantages to this model, but for different types of terrain, because this model has only considered some specific type of terrains, so depending on the variations in terrain, if there is a fast variation in terrain, so generally this model does not give very good results. Common standard deviations that are observed with these models, so if we take actual measurements and we predict using this Okumura model, so generally the standard deviation comes in the range of 10 dB to 14 dB. So this is the common standard deviation that we get from this model. So this was the introduction related to this Okumura models. Let me quickly go back to this expression. So if in order to calculate the total path loss in any type of environment, what you need to do is to first thing is to calculate the free space path loss LF, which is calculated from the free space path loss formula. Then second thing is to calculate the median attenuation with reference to the path loss, which is calculated from the curves generated by the Okumura. Then you need to calculate the correction factors related to base station antenna height and the mobile station receiver antenna height. And last thing is to include the effect of the terrain by taking the specific type of environment into consideration. So by using these things, we can calculate the path loss from this Okumura model. Let us take a simple problem on this basis. Find the median path loss using Okumura's model for a distance of 50 kilometers. So we are given a distance which is 50 kilometers. The transmit antenna height is given as 100 meters. Receive antenna height is given as 10 meters. So 10 meter is the receive antenna height, and the type of environment that we are given is suburban environment. So we want to find median path loss based on this Okumura's model. So as I discussed, the first thing that you need to calculate is the free space path loss which occur with this particular type of environment. And if you recall, the free space path loss formula is given by this expression. This we have discussed when we were discussing the free space path loss. Alternatively, you can directly use the free space path loss formula in decibels. We also discussed an alternate formula for free space path loss to calculate the loss in decibels directly. So you can take this formula. This 10 log factor which is shown here, of course this is the free space path loss. We have taken log and multiplied by 10 in order to represent the entire thing in dB. So this is the decibels. So this 4 pi square is constant, so they have constant values. D is given as 50 kilometers. So in this formula we have substituted 50 into 10 raised to power 3 whole squared. Lambda is the wavelength which is not mentioned in the problem, but we are given the carrier frequency of 900 megahertz, and we can use that 900 megahertz carrier frequency to calculate the wavelength, and we know that lambda is actually equal to the speed of light divided by its frequency, c upon f. So this lambda is actually c over f. C is 3 into 10 raised to power 8 and f is 900 into 10 raised to power 6 whole square. And if you simplify this entire thing, you will see that the result is 125.5 decibels. So this is the path loss that occurs when you are considering the free space propagation only. But for this particular case, actually we do not have free space propagation, so we need to calculate the other factors as well. So second part is to calculate the median attenuation from Okumura's model, this AMU, and as I discussed that this free space attenuation is dependent on this median attenuation is dependent on distance as well as frequency. So we want to find this median attenuation when the operating frequency is 900 megahertz and the distance of propagation is 50 kilometers. So in order to do that, we have to go back to this curve. This is the median attenuation curve as developed by Okumura. In this curve, you have to identify the 900 megahertz frequency. Actually, you have this numbering here. The horizontal axis is representing the frequency, and you can see that we have the 900 megahertz frequency would be somewhere here, of course below 1000, so it would be around somewhere here. Similarly, the 50 kilometer distance is this value, so this curve is actually representing the 50 kilometer distance curve. So you have to note the path loss from the median attenuation from this curve. So if you take a line from this 900 megahertz and then take it to this this variation, it should be straight line. So if you take it here, so it would come up somewhere here. So this value would represent the median attenuation. So this is actually between 40 and 50 is below the half, so you can take it as maybe 43 or 44 decibels. So this median attenuation from Okumura curve comes out to be 43 decibels when the operating frequency is 900 megahertz and the distance of propagation is 50 kilometers. The third thing that we need to calculate is the effect of terrain or area. So this area, this need to be calculated from the Okumura's curves as well. So if we go back to the Okumura curve for suburban environment, so this is the curve here. Again, you have to locate the frequency, which is 900 megahertz. It could be somewhere here. So from here you can you can draw vertical line up to the suburban area curve here, and then you can read the value from this vertical axis. So this correction factor because of the terrain comes out to be around 9 dB. So this correction factor is almost 9 dB when you read from the curve. So next thing in the Okumura's model is the effect of the antenna heights. So we have certain antenna height for base station, which is given as 100 meters, and we would have certain antenna height for receive antenna or mobile receiver, which is HRE, which is 10 meters. So these effects should be calculated using the formula that we have discussed here. So because HRE we have used as 10 meter, so we have to use this formula. For gain of receive antenna, and similarly we have to use this formula in order to calculate the gain of transmit antenna. So let us calculate these two. So this the correction factor because of the height of the transmit antenna comes out to be this value, which is 100 upon 200, which is minus 6 dB, and for received antenna this comes out to be 10.46 dB. So we have calculated all those parameters which are included in the path loss formula for the Okumura's model. So in order to calculate the median path loss, the total median path loss is given by this formula: L50 dB is equal to LF plus AMU plus FD. So LF is 125 dB, AMU which is median attenuation is 43 dB, GRE is minus 6 dB, GHRE is GHTE is minus 6 dB, GHRE is 10.46 dB, and G area is minus 9, and you get a total value of 155.04 dB as a total loss occurring because of this environment. Okay, so we take the second part of the problem. There is another thing asked in the question. So if the base station transmitter radiates the EIRP of 1 kilometer, so we know that the EIRP is 1 kilowatt for the base station transmitter. We want to find the power at the receive antenna, and we are assuming that the receive antenna has unity gain, so it does not have any other gain. So received power, if you recall, we have discussed it previously. The received power is dependent on three terms. First one is the EIRP of the transmitter, which is given here, EIRP of in dBm, minus the loss which you encounter during propagation, which we have already calculated here using the Okumura model, plus the gain of the received antenna height, which is here, but as it's given as a unity gain antenna, so in decibel this gain will be 0, because log of 1 is 0. So this receive antenna gain is actually 0. So receive antenna gain is 0. L50 dB is already calculated as 155.04 dB is shown here. EIRP, we are given EIRP in kilowatts. We have to transform it into dBm, and we have done some problems previously in order to transform EIRP into dBm, because dBm means you are taking the reference value of 1 milliwatt and you are calculating EIRP. If you calculate EIRP using that formula, means converting this 1 kilowatt into dBm, you would see that the EIRP comes out to be 60 dBm. So we know all three terms here. EIRP is 60 dBm, the loss is 155.04 dB, and the receive antenna gain is 0 dB. So if you simplify, you would see that the overall received power will be minus 95.04 dBm at the receiver side. So you have calculated the received power at the receiver side using this simple relationship between transmit power and the received power. If you want, you can convert it back to the kilowatt, but for our problem it's sufficient to calculate the received power in dBm. So this was a discussion related to the Okumura model. So let me quickly summarize. This is the main formula of the Okumura model, and we have individually discussed each term in that formula. We have individually how to calculate this term, and we have also taken a problem, how we can solve a problem on the basis of Okumura model. So we stop our discussion at this stage. We have in today's lecture we have discussed a measurement based outdoor propagation model, which is named as Okumura model. There are some other models, but we are not going to discuss them in detail, although I'll give use some formula related to some commonly used model, but will not be discussing them in detail. So we stop our discussion here. Inshallah, we'll continue this topic in our next lecture. Thank you all.